welcome to our second class that's not live, hopefully the last one in this case. This will be the second class that you'll need to complete the homework assignment that was already posted on the course website. So please make sure that you review both the videos for last week's class as well as this video, and it should give you all the material that you need to complete the homework assignment that is due on March 8th. Moving now towards what brings us today, we're going to be talking about Introduction to Observational Studies. So last week, for instance, we were looking at randomized controlled trials and everything that evolves around them, right? We talked about why they're considered the gold standard in terms of causal inference, and why they're used a lot of the times as the benchmark to identify causal effects. We talked about how to analyze RCTs in practice. We played with data, randomized different treatment assignments, see how balance works in a randomized experiment. So all those things are tasks that you should be able to complete. So please also look at the code that we reviewed in class and the code that's attached to the slides. There's a lot of other questions that are embedded in those codes. So again, try to work through those, play with the data, and try to come up with answers. If you have any questions, please feel free to reach out as always. We also talked a little bit about the assumptions and limitations behind RCTs. So the idea here basically is that even though randomized controlled trials have very high internal validity in terms of being able to identify causal effects for the sample at hand that we have in a field experiment, a lot of the times comes with certain limitations in terms of external validity, for instance. In that sense, if you don't address those concerns from the design stage, it's much harder to try to fix that post hoc. So you should always have in mind that when you're choosing a sample for your randomized controlled trial, try to make it as similar as possible to the population of interest that you have in mind, and for the population that you want to make inference on. We also talked about the assumptions behind RCTs, such as SUTVA. So a lot of the times we're assuming that there's no interference between units, which again might be a stretch depending on the field experiment that you're running, and should be something that you consider and actually include in your analysis if you're not sure that SUTVA actually holds. In the other hand of the limitations, we talked about attrition and non-compliance and how you could actually try to ameliorate those limitations, but those are problems that usually arise when you're running field experiments, so it's definitely something that you should keep in mind. One limitation that I did not mention on the last class, but it should always be at the forefront of your thought process when you're designing a field experiment, are ethical concerns with the treatment that you're assigning. A lot of the times that is not feasible to randomize an intervention, but a lot of the time it's just not ethical. Okay, so randomized controlled trials have come very critically inspected in that sense, because a lot of the times with our obsession for causal inference, we tend to leave aside certain ethical concerns regarding whether we're causing harm or not by conducting certain field experiments. So again, just keep those things in mind when you're even designing or looking at the data in a randomized controlled trial. Finally, we also talked about statistical power, how does sample size play a role in that sense. So even though we can detect causal effects in a randomized controlled trial, if all the assumptions that we talked about hold, a lot of the times we just don't have enough sample size, for instance, to actually detect effects that are very small. So sample size plays a huge role in that sense, and we should be able to identify what sample size we need in order to detect effects of different sizes. We also talked about randomized inference, and as someone also mentioned in the JIT, basically this gives us a way to identify exact p-values. So instead of relying on the properties of large samples in this case, we are actually estimating the exact type 1 error that we're willing to accept. And in that sense, also because we're looking at the very tail of the distribution in this case, when we're talking about the lady tasting tea example, for example, that also gives us a view on what the statistical power of our test would be in that scenario. Changing gears a little bit, today we're going to be talking about the introduction to observational studies. So we're going to talk about whether we can identify causal effects without RCTs, what the assumptions behind those things are, and also we're going to compare two different adjustment methods in this sense, which is matching versus regression, the typical regression analysis we've been looking at so far. So let's get into this. So a lot of the times, as you might already be aware, we're actually not able to randomize, and we need to work with existing data. Okay, we might not just have access to randomizing the intervention. We might work with data that has already been generated and is passed, and we don't have time, for instance, to actually run a field experiment and collect more data. So most of the analysis that we do actually in causal inference relies on data that is already out there, which we will call observational data. And analysis that we do with observational data are observational studies. Observational data basically means data for which we can't manipulate the treatment assignment, or where the treatment assignment basically wasn't manipulated in a known way. So basically it's data in its natural state. So any sort of data that is generated just out there in the world would be considered observational data. Administrative data, data that's collected by a lot of companies where they don't actually randomize any sort of treatment assignment, all of that is observational data. The thing here is whether we can reasonably assume that in observational data, the ignorability assumption holds. So if you remember from last class, the ignorability assumption is basically the cornerstone to identify causal effects, where we're assuming that the potential outcomes don't actually relate or are independent of the treatment assignment. With RCTs, it's very easy for that assumption to hold because basically we are designing the treatment assignment. In this case, we're not. A black box basically generated that treatment assignment, and we're seeing whether it's reasonable to assume that in that case, the ignorability or independence assumption holds. So for this part, we're going to move away from the core assumption of RCTs, basically that the probability of the treatment assignment is a known function. So as you recall, on the previous class, we designed the treatment assignment. So clearly we knew exactly what the probability for each unit was to get the treatment or not get the treatment. In this case, we want that probability will not be known, and we will have to estimate it to the best of our abilities. An important thing that I should mention, that the probability of treatment assignment is a known function, doesn't necessarily mean that everyone has exactly the same probability of being in the treatment and the control group. Okay, so it doesn't necessarily need to be a 50-50 chance in that sense, but it needs to be a known probability. So that's something important. You don't need to assign a 50% and 50% to treatment and control. You could perfectly do 2/3 and 1/3. In that case, the probability of assignment would be 1/3. You could try to prioritize certain people or certain units into treatment. That is also does not break the assumption of randomization. The only thing is that we are designing the randomized assignment in the case of field experiments, and we know that probability function. So now in observational studies, we will again move away from that core assumption from RCTs, but we will maintain the assumption of unconfoundedness to a certain extent. And you might be wondering what unconfoundedness is. So basically, unconfoundedness a lot of the time works a little bit interchangeably with the independence assumption to a certain extent. So basically it means that the treatment assignment is independent from the potential outcomes, which again sounds very similar to what we already saw with the ignorability assumption, independence assumption, exchangeability assumption. All of those names are kind of interchangeable. Okay. Unconfoundedness, however, it's a little bit broader in the sense that a lot of the times it assumes that we have conditional independence. So it does not need to, the potential outcomes do not need to be independent of the treatment assignment unconditionally, but they could be independent of the treatment assignment conditional on certain covariates, okay? And that is called the conditional independence assumption, which is basically what we'll be using now for observational studies. So again, the ignorability assumption in this case, this first one here, it's a bit stronger, basically because I'm saying that for all the units in the population, the potential outcomes can be related to the treatment assignment. With a conditional independent assumption, what I'm saying is for all units that have similar characteristics, or the same characteristics in this case, values of x, for those units, the treatment assignment needs to be independent of the potential outcomes. So basically, it's a bit of a weaker assumption in the sense that we're just looking at a homogeneous population in terms of covariates. So the assignment mechanism, and this is somewhere that I want to stop a little bit, it's basically the key component of causal analysis. So in randomized controlled trials, as we already discussed, the assignment mechanism is known. It's actually designed by the researcher. So we know exactly how it behaves, how it works for every person. But in observational studies, the main problem is that that assignment mechanism is sort of a black box. So what do we do in that sense when we don't know how people were assigned or self-selected to a certain extent to the study? So in this first chapter here, we are going to consider 3 assumptions that are key in terms of identifying causal effects and working with the assignment mechanism. The first one, we're going to assume individualistic assignment. We're going to assume a probabilistic assignment. And finally, we're going to assume an unconfounded assignment. So the individualistic assignment, basically what it says is that it limits the dependence of the treatment assignments for a unit, I, on the outcomes and assignments for other units. So again, this might sound kind of similar to SUTVA to a certain extent, which basically means that the probability of assignment to unit I, to an intervention, to a treatment, okay, that's PI, it's a function exclusively of its own covariates and its own potential outcomes. So again, it does not depend on the potential outcomes of other units, and it does not depend on the covariates of other units. So again, this sounds pretty similar to SUTVA to a certain extent. From last class, one of the questions that I wanted to pose, and hopefully you can think about them, and if you don't know the answer, you can get back to me. But think about an example where this you think doesn't hold. Particularly, we talked about a specific way of randomizing treatment when we're talking about the A/B testing chapter. And there's one of the mechanisms that we talked about that in this case would not necessarily comply with the individualistic assignment assumption. So look into that, and you can get back to me if you have not guessed which one it is. In terms of probabilistic assignment, basically what this assumption means is that every unit has a non-zero probability of each treatment value. So basically this means that everyone in the sample that we're going to analyze has a probability different from 0 to be either in the treatment group or in the control group. Okay, so this means that there's no individual or unit that is deterministically is going to be in one of the 2 groups. That in that case would break the probabilistic assignment. And basically this means that everyone has a chance to be either in one of the 2 groups. When could this assumption fail? Basically when we have a certain group, for instance, that will always be treated. Imagine that you have an intervention that is targeted exclusively or more consistently towards a lower income individuals. Then you might think that the individual that is at the very bottom of the income distribution will just always be treated. Okay, then the other ones might have a probability different from 0 and lower than 1 to be treated. But for those people or those units, this probabilistic assignment would hold. But for units that will always be treated because they're always at the bottom, for instance, of the distribution, then they deterministically always would be on the treatment group. That generates basically a problem because if there's a group that deterministically goes into either the control or the treatment group, that means that you don't have a good comparison in the other group. So that will generate a problem for estimating solid counterfactual. And finally, the unconfounded assignment, it's very similar to what we've talked about, the unconfoundedness assumption in general, which basically means that the assignment mechanism does not depend on potential outcomes in that sense. So if you think that you have a vector of treatment assignments in this case, so again, C is a vector of treatment assignments for all units I from 1 to n. If this is conditional on the covariates of the units and the vector of potential outcomes, if I change those vector of potential outcomes, basically the probability stays the same because they're independent from each other. And this is basically for all possible values of the treatment assignment, of the covariates, and the potential outcomes. So basically all that I've been talking about so far leads to one sort of term that's going to be, that we're going to assume repeatedly through this chapter in particular, which is selection and observables. So I'm assuming that units select into treatment or into control groups based on characteristics that I can observe. And when I say characteristics that I can observe, I mean characteristics that are in my data. It doesn't mean that I can observe, like physically see whether that woman is female or male or something like that, but I need to be able to code it and incorporate it in my model, okay? So in that sense, everything that's on my data set will be something that I can observe, and I'm assuming that every way that the units select into treatment or control group, I can observe within my data. So this means that if I have, for instance, two different observations in this case, both with a vector of potential outcomes that, again, I cannot observe. One of them is assigned to treatment, one of them is assigned to control group. They have two different outcomes. If under all these three other assumptions that we saw before, if those two observations have exactly the same covariates, in this case x sub f, then I would assume that between those two, the treatment assignment was basically as good as random. So as we had discussed before when we were talking about confounding on already 2 weeks ago, I guess, the main issue that we have right now is how do we adjust for observables. Remember that confounding is only a problem if we don't adjust for the confounder. So we can observe the confounder, we can adjust for it. So basically in this case, in selection of observables, we have no problems of confounding because we will incorporate those variables into our model. So one way that we can adjust for observable characteristics, very straightforward, is a regression analysis, right? We've already seen this, where we have the outcome of interest, the treatment assignment in this case, and some characteristics of the unit I. If I control for those, and I'm assuming unconfoundedness, then beta 1 will have a causal. I can make a causal claim on that coefficient. So I already mentioned this. Under unconfoundedness, basically we would interpret beta 1 as the effect of the treatment C on the outcome Y. Okay, but again, this is only under unconfoundedness, thinking that x, that vector x of characteristics is all I need in order to break the link between any confounding variable and the treatment. And beta 1 again is the effect of the treatment C on Y, again holding the characteristics x constant. The main issue that we have with regression analysis, however, is what happens if our data looks like what I have here. So as you can see clearly, I have the outcome, I have a variable x here on the x-axis, and I can see that I have two distinct cluster of units, right? The first one was treated, was on the control group, and the second one was treated. The main issue with regression is that actually a regression doesn't impose any restrictions for overlap. So in that sense, it works a lot with extrapolation. and means that if I run this model, the previous model, for instance, that we saw on the last slide, this would actually give me a result, and I will be able to identify the treatment effect beta 1 as the difference between those two regression lines. So again, the dashed purple line would be the fitted regression for the control group. The dashed yellow line would be the fitted regression line for the treatment group. And the difference between those lines is a constant, which is beta 1 in this case. And as you can see, even though there's absolutely no control units on this part of the distribution, I still am able to extrapolate my regression line to this area of the distribution, and the same with the treatment line. Okay, this is basically because regression analysis works a lot with extrapolation. It takes sort of a weighted average of what your counterfactual would be, and it doesn't matter if that there's no actual support for it. It would still be able to estimate an effect outside of the support vector of that sample. So in this case, you might be a bit wary of whether this makes sense or not. You have clearly two very distinct groups, and regression analysis just doesn't put any restriction on the fact that they need to look a little bit somewhat alike, and I don't want to fully rely on extrapolation to estimate an effect. So this is basically where other methods come in, such as matching and weighting. So basically what we want to do now, instead of relying on regression analysis, is that we want to find similar units in one of our samples and group them together with similar units that are in the other sample. So if you think about the treatment and the control group, I want to take units of the treatment group, find basically matches or similar units in the control group. So there are different ways to do this. They're all kind of similar in that sense, but you can think about subclassification or you can think about matching. And matching is a very broad term because there's a lot of ways that you can do matching, as we will see. So one of the main questions here is, okay, this is great, but what do we gain in this sense? The first main advantage of a method like matching or subclassification, for instance, it's that it reduces model dependence. So again, unlike the regression analysis where we were very dependent on whatever model we were fitting in that sense, this can work what we call non-parametrically, which basically it's free of any model assumptions to a certain extent. The main problem is that if there's imbalance, there can be model dependence. If there's model dependence, there's a lot of researcher discretion in what model to fit in that case, and that again can lead to bias. There's a big problem a lot of the times with cherry picking results or trying to find causal effects more than not find causal effects. So for instance, a researcher can be prone to choose a model where you find an effect versus a model where you don't find an effect. And again, you don't know which of those two models is actually the true model in this case, so that generates a clear problem. One of the second main advantages is that in matching, we're comparing like to like. So we're taking units in the treatment group, for instance, and finding units that are very similar to those units in the control group. So in that sense, you're comparing two units that are very closely related in terms of observed covariates. So if you think about this, it's kind of trying to recreate to a certain extent what the ideal randomized controlled trial would be. Okay. Again, we don't have a randomization in this case, but if we're thinking about unconfoundedness, you're comparing two units that are very similar to each other. And also because of that, we don't rely on extrapolation. Matching, on the other hand, only relies on interpolation within the units that they match, okay? And finally, we can also adjust closely by covariates. So again, unlike the example that we saw with the regression analysis, where we have two groups that are clearly very different in terms of a covariate value, and regression still sort of gives you a result. In this case, I can tell my model or tell my analysis how closely I want those units to resemble each other. And we will see that with any sort of balancing restriction that we pose. So in that sense, we have different types of matching, such as exact matching, which, just as the name sort of refers to, is matching exactly on certain characteristics. We have coarsened exact matching, which was proposed, or a big advocate for it is Gary King at Harvard, where basically they coarsen the covariates to a certain extent and then try to exact match on those coarsened covariates. We have fine balance, where we can actually match the categorical distribution of covariates. So again, there's a lot of room to play here in terms of how close we want to adjust for certain covariates, depending on our goal. So talking a little bit, for instance, about model dependence. I want to show this example because I think it's very telling on what the main problems of regression analysis can be in terms of depending very strongly on a parametric model. So imagine that we have, in this case, observational data, and we have the outcome for an intervention of interest, and also we have a covariate, and in this case would be years of education. Some of these units were treated. For instance, you can think about an information treatment, and some of these units were not treated. So as you can see, even though there is overlap in this case, in this region here, the bottom and the top of the distribution actually are only in the control area. So if we feed a very simple model, like one of the most simple regression models that you might think of, we might just regress the outcome on education and treatment. And as you can see, we find this, we can fit these two lines for the treatment and for the control group in this case, and the same as before, the difference between these two lines are going to be my treatment effect for that population given this level of education. In this case, we're assuming that there's a constant effect, which will be beta 2, and for every level of education, the difference between the two lines is the same. What happens, however, in this case, if we include a quadratic term of education? This, again, if we see the relationship does not look very linear, so maybe it makes sense to incorporate a higher level polynomial in this case. And as you can see now, basically the distance between those two lines is reduced considerably. So again, which one is the true effect? Is it beta 3 in this case, or beta 2? In the first model that we fed it? They're very different. So again, if I don't have a clear notion of what the true underlying model is, then I won't know what the true effect is either. But now what happens if we just focus on the region that is more on the overlap section? So basically this, where we have both treated and control units. As you can see, if I fit now the same model that I fit on my first try, the effect that I find, that beta 2 now, is very small, right? You can see that there's barely any sort of treatment effect. So maybe that is the true treatment effect, at least for this population. Again, this is not the treatment effect necessarily for the entire sample that I had, but it might be the treatment effect in this case under certain assumptions for the population that I'm using. The good thing now is that if I include the quadratic term in this case, for instance, you can see that the treatment effect remains basically unchanged compared to the use of just the linear term of education. So this is sort of reducing model dependence, because I'm just using that overlap region between the treatment and the control group in terms of education. So the main question here is, how do we know that we can remove those observations? is it is actually useful to do so? What are some of the things that I'm missing in that sense? Does it have advantages or disadvantages? Clearly, it seems to have an advantage in terms of model dependence. Maybe it has disadvantages on other areas, as we will see. So now going into the ways that we can actually do this in practice. So I wanted to start from the very sort of high top, the most coarsened way to compare like to like, which in this case will be subclassification. Subclassification is very similar to the idea of stratification that we saw in the previous class. So basically what it means is that I'm going to group units depending on their similarities of characteristics, and then I'm going to compare, estimate the effects for each of those different strata. So in this case, I have three covariates. I will have x3, which is a continuous covariate in this case. I have a binary variable, which is x1, and you can identify the units that have x1 equal to 0 or x1 equals to 1, depending on their shape. And then I have a covariate x2, which is a categorical covariate, and it has basically 3 levels. And you can distinguish them by color. So for instance, this unit right here, it has a value of x1 equals to 0, a value of x2 equals to 1, and it has a very low value of x3, okay? While this one up here has an x2 value of 3, an x1 value of 1, and an x3 value pretty high up in the distribution, okay? So this is the idea. In this one plot, we are basically showing a lot of information, 3 different covariates and the outcome. So the idea of subclassification basically is to build a combination of whatever covariates you want to balance on. So in this case, for instance, I might only be interested in balancing by x1 and x2 directly. So what I do is basically build a combination between those 2 variables. And because one of them was 2, the other one was 3, the combination of both will be 6. So as you can see here, I have 6 different strata. I have value of x1 0, value of x2 1, value of x1 1, value of x2 1, etc., etc. And as you can see, basically the different colors will be identifying a different stratum. So what I do afterwards is just compare the effects within stratum. So I'm imagining that x3 in this case doesn't really matter. Maybe it's not a confounder. It's just a variable that is there, but it's not necessarily affecting my treatment. So I'm assuming that only x1 and x2 are the variables that could potentially lead to confounding. So in this case, if I look at the first stratum, I can see that I have units in the treatment group and, in the control group and units in the treatment group. I can compare it through them. The same thing with strata 2, 3, 4, 5, and 6 in this case. And again, triangles in this case are identifying units in the control group, squares are identifying units in the treatment group. So I have a lot of mini sort of as if randomized controlled trials in this case, because again, I'm assuming unconfoundedness on x1 and x2. And I can estimate treatment effects for those small strata. So how do I estimate the average treatment effect for the whole population? This will basically be just a weighted average, okay? So if y bar is the average for the treatment group on stratum S, and y bar 0 is the average of the control group in stratum S, then basically I can just get the difference of the 2 samples within a specific stratum, and then what I do is just weight it by the number of units that I have in that stratum. So basically that means that a stratum that has a larger number of units will weigh more than a very small stratum, so they're not weighed the same. So the estimation of the average treatment effect in this case will be a weighted average of those smaller average treatment effects in that case. One of the problems here with subclassification is what happens when we have actually too many variables to build strata. There's something called the curse of dimensionality, which basically means that when you have too many covariates, and not even too many, but even a reasonable amount of covariates, the number of strata or groups that you can combine actually grow exponentially. So for instance, if you just had 4 covariates and each had 5 categories, then you would have 625 combinations. This is clearly a problem because 4 covariates with 5 categories each is not a lot. It's really not a lot of information in that sense. And you already have 625 combinations. So that means that in order to actually estimate average treatment effects for each of these different strata, you would need at least twice the number of observations in your data to actually be able to estimate anything. And you will need to have at least 2 units, one in a treatment and one in the control group, to actually estimate an effect for that strata. If you don't have a treatment and control unit in each stratum, then basically you can't estimate an average treatment effect, and you would be losing that stratum from your sample. The other problem, of course, is that at least you need 2 units in each stratum, but actually you need a bit more because you want to also probably estimate standard errors, right? You want to look at sample variability and things like that. So as you can see, it's easy to see how your sample size would have to blow up if you wanted to use some sort of subclassification in this case. So what can we do in that sense? So in order to break the dimensionality, the curse of dimensionality, we have what are called balancing scores. So basically what this does is create a score or an index that reduce the dimensionality of our covariates. So the idea is to, within one number or one variable, try to collect all the information of the covariates that is related to the treatment. So again, the idea is to try to reduce the dimensionality of this, so we don't have so many strata to think about, but we just have maybe one number that will be enough to collect all that information that we need. So in that sense, a balancing score, it's a function of the covariates, okay, such that when I condition on the balancing score, I'm collecting all the information that is related to confounding in the treatment assignment. So the idea is that conditioning on that balancing score is enough to actually remove bias associated with the covariates. So if you're thinking about adjusting by covariates, this would be the same as adjusting, in this case, by the balancing score. So again, in terms of confounding, the balancing score has all the information that I need. So under unconfoundedness, the idea is that if I condition by the balancing score, then again, the treatment assignment is independent of the potential outcomes. So remember that before, instead of conditional about the balancing score, we were conditioning on a vector of covariates. Now I'm just conditioning on one number. So again, this reduces sort of the dimensionality and makes our lives way easier. One important thing to remember is that actually there's different balancing scores. It's not one out there. The most common one that you might have heard of is the propensity score, but actually you can think about Mahalanobis distance or other types of distances. There's a lot of ways that you can use a balancing score in that sense to achieve the same thing. So within the most famous, I would say, balancing scores is propensity score. So you probably heard about this. Basically what propensity score is, it's the probability, it's a model for the probability of being in the treatment group. So in this case, how do we estimate the propensity score? We basically run a logic regression. So this is very similar to what we saw already in our dependent binary dependent variable class. So here we have the log odds of the probability of being in the treatment group as a function of the different covariates that we think are affect that treatment assignment. So again, the only difference here is that in P, instead of being the probability of success or y equals 1, is the probability of being in the treatment group. basically z equals 1. Okay. How do we do this in practice? Again, it is the same thing as a typical logistic regression that we've seen a bunch of times. In this case, we run a generalized linear model with the same function that we would do for a typical logit, but now the dependent variable is the treatment assignment, so it's z, okay? I use the family binomial length in this case, and because I need to predict the probabilities, I need to again write type equals response in this case. One important thing of balancing scores in general, but also that is very highlighted in propensity scores, is the importance of what we call the overlap region. So remember that on the regression analysis that we saw with the education covariate and the treatment assignment, remember that there were just groups of control units that did not really overlap with treatment units. In that sense, that overlap region is going to be key to identify where I can get my matches from. So for instance, imagine that the purple distribution here is the control group and the orange distribution here is the treatment group. This is the distribution of their propensity scores, basically their probabilities of being assigned into treatment based on their covariates. So in this case, for instance, you can see that clearly the control group has a lower probability of being in the treatment group. And it's obvious, it has different characteristics, and again, they're more likely to be in the control group, while the treatment group has a higher propensity in general, right, on average. But again, there is variance among this, which is what we will use to match these different covariates. So in this particular case, we'll be focused on what we call the overlap region, which is basically this region right here, where we can obtain observations that have the same or very similar propensity scores, but are on two different groups, either the treatment or the control group. This basically means that matching in general will not work for units, for instance, that are in the very outskirts of the distribution. So in this case, for instance, most likely I won't be able to find good matches for control units in this part of the distribution, basically because I don't have anyone of the treatment group that has such a low propensity score. And in the same sense, probably I won't be able to find very good matches for the treatment units over here, because there's really no control units that have such high propensity scores. So in that sense, again, my analysis will be limited to the overlap region, basically where I can find both treatment and control units with a similar propensity score. Another important balancing score is Mahalanobis distance. So basically what this is a vector of distances that uses the deviations from the mean. So in this case, mu is a vector of the sample means for each covariate, okay? And x is the vector of covariates for a specific unit I, for instance. So basically what this is measuring is how far is this observation in terms of covariate from the average sample. And we are actually modulating that by their covariance matrix. So this is incorporating the knowledge that covariates are not independent from each other, and there's actually covariance associated with them. So there could be two observations or two variables, better said, two variables that actually move together very closely, right? Because they have a they're very similar and their covariance is very high. So in that sense, those differences are not going to be weighted the same way, basically because those two covariates are not providing the same information. If I match on one, it's probably going to be very closely matched on the other one because of their high covariance. So this is incorporating all those all that information. Not only taking the raw distances, but modulating them by the covariance between and the correlation between the different characteristics. How do we do this? It's very easy. For instance, you can use the Mahalanobis function in R. It's just, you don't need any additional packages. And when you need to give them, it's a vector or a matrix of covariates, the mean vector of characteristics, in this case, the column mean or the column average, in this case, of the matrix of covariates X would be mu. And then also the covariance matrix S, which in this case you can get very easily with the covariate function. In the same way, you can use a rank-based Mahalanobis distance matrix, which is the same, but basically what it does, it also rank the distances. So again, we can use kind of like an absolute measure in that sense to do the matching. And you can construct that very easily with the design match package. And in this case, you just have to give the function dismat, the vector for the treatment assignment, and the matrix of covariate. And you will get your Mahalanobis distance. You can use both of them in R very easily. You don't need a lot of the times to construct this separately. You can just use them within the matching package, as we will see when we start playing with R. Okay, so we talked about subclassification, we talked about balancing scores and how they work. So one thing that you could think about is that you can use balancing scores actually as another covariate, right? So you can use it just to incorporate it in a regression. But that, again, misses the point of the fact that we're trying to lose model dependence. And we're trying to find and compare like with like. So what we can do actually is match observations between treatment and control group that have similar values on their balancing scores. We also will talk a little bit about that you can also match balance covariance directly. It's a bit harder in the sense of computational power, but again, it works a little bit better. So in any sort of matching in this sense, there are going to be two steps. The first step will be pre-processing, which basically means that we're going to try to model the treatment assignment in a certain way. So again, we don't know what the treatment assignment is, so we're going to use certain assumptions and informed guesses in that sense. So all the variables that you think might affect treatment assignment should go into your model in this case, or in your balancing restrictions to a certain extent. And the second step basically is just estimation. So we will now use that trim or pre-processed data, and we're going to build a model and calculate difference in means. Again, we don't need to actually run a regression with this. We can do it non-parametrically, just calculate difference in means, run pair t-test, etc., etc. So one of the questions here also might be how matchy-matchy needs my sample to be. So there are a lot of different matching methods and different ways to use them as well, as we're gonna see. One of the most common ones, which was one of the first to appear, but it's one of the least precise ones to a certain extent, is nearest neighbor matching. Nearest neighbor matching, what it does, basically, it takes units and find locally the closest unit in terms of balancing scores. Okay, so in that sense, it takes your first treatment unit and it goes through all the control units and find which one has the most similar balancing score and assigns that to that first unit of treatment. Then it moves to the second one and does the same thing, third one and does the same thing. So as you can see, this will generate a sample that is closely matched in terms of balancing scores. But because this is a greedy algorithm, it's not globally optimized. In that sense, what it means is that because it only optimizes locally in the sense that it goes to the first one and finds the closest match, then moves to the second one and finds the closest match, that means that if you shuffle your data differently, you might get a different result. Okay? Basically because it's only optimizing locally for each of the units, and it matters which order it's allocating the different control units to the treatment units. So that's not great because you hopefully want to get the best answer out there and not just the best answer for whatever order of your data you have, right? In that sense, optimal matching comes in, and basically this solves a global optimization problem. So again, not just locally for one unit at a time, but takes the whole thing and basically minimizes, for instance, the distance of balancing scores between the treatment group and the control group for the matched units. One of the main problems here, and it will be a problem for most matching mechanism in this case, is that it's very slow on large samples. So actually one of the examples that we're going to be looking at, we won't be able to actually run optimal matching because most computers basically can't handle the amount of computer power that it takes. Which is a shame because, again, it's a good algorithm in a sense, but works well on smaller samples and not very large samples. And finally, one that I wanted to talk about, because it's basically one of the things that I do, is mixed integer programming matching. You might have heard of the first two, for instance, if you had any sort of proximity with matching. But the third one, it's been around already for a while, over 10 years, I would say. And basically what mixed integer programming matching does, it solves an allocation problem, but a lot of the times it does it way faster. Mixed integer programming matching does not need a balancing score, so you can balance covariates directly, which will be a huge benefit. We'll see that balancing scores, just very similarly to RCTs, generate balance on expectation, but doesn't assure any sort of balance with your sample at hand. While matching actually can balance covariance directly and can comply with any balancing restrictions that you propose in that sense with the sample that you have. Because a lot of the times it does have more restrictive balancing restrictions in that sense. So you want to match units more closely, for instance, and you're not just balancing one score in expectation. It can generate smaller samples, but also, especially in the new development, one of the advantages is that it works much faster, for instance, than optimal matching. And even with very large samples, you can actually get a very well-balanced group. So now let's go to R and look at some of the great examples that we're going to be playing with today.